Wow. I guess we're live. Good morning, good afternoon, good evening, no matter where you are around the world. Welcome to Kilroy's World. I'm Al Forte. Welcome to my office. I guess. Oh, I guess that's the PowerPoint. We're going to talk today about transformers and inductance. And let me go ahead and fire up the PowerPoint and get started on it because it's going to be a long PowerPoint. If I can find it, hiding behind my camera. I hope everyone's doing well out there. My chat is down over here, and it just let's see, it swapped that out. It's one thing after another with this computer over here. I tell you, it's just the pits. Maybe I can catch the chat on here. Maybe that's what I'll do. So in the meantime, I guess what you need to do, or what you can do, is make sure you have some nice coffee to sip on. I kind of learned that from another YouTuber by the name of Paul, who always starts at, "Hey, I'm listening to myself." So in the meantime, let's be quiet, guy. Be quiet. 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 I kind of learned that from another YouTuber by the name of. And of course, it's not letting me get to the chat. Let's see. Let's see. There's the chat. No chat. Report. Quality. No. Report. No. If this thing over here would work, we would have some chat interaction. If not, I'm going to have to figure out how I'm going to get the chat. Maybe I can just minimize this over here and see the chat over here. Yeah, I think that'll work. I think that'll work here. I'll just do it that way. Anyway, and I'll bring up YouTube over here. So, hello out there to Ruben. How you doing, man? Before you get started, I want to let you know ARC won't work for now. Oh no! Internet is down using phone as a hotspot. Yeah, that you definitely need a little. I think a little more than phone for hotspot. But wow. But at least you have something, right? Hello. When a girl has no name, Lady Frenzy Wicked Truth from Twitch. She's a trisexual. Oh no, I just messed that up, didn't I? Tristitual streamer over on Twitch as a Lady Frenzy Wicked Truth. Okay, so I have chat going, and as you can see behind me is the whatever that's called behind me, the PowerPoint. Let me go ahead and change it back to where I'm small. Now I'm tiny, little bitty tiny in the corner. And I'll go ahead and talk about some of the things. Yeah, I can do this way. Some of the things that we're gonna talk about. We're gonna cover induction, alternating current. We're gonna talk about self-induction, or L, self-induced voltages, which is V sub L. We're going to talk about how V sub L opposes a change of current, how mutual inductance works. We're going to talk about transformers, and we're probably going to spend a lot of time on transformers, but it all kind of melds together, you know, as to what inductance and transformers are all about. We're going to talk about transformer ratings, impedance transformers, core losses, types of cores, variable inductance, inductances in series and in parallel. Yeah, and you can have inductances in series and parallel just like you can resistances, energy and magnetic field of inductance, stray capacitance and inductive effects, and measuring and testing inductors. And with that, we'll talk about induction by alternating current. So if any of you have any questions, let me go ahead and make sure I got the chat back up here. Please don't hesitate to say it. Hey, look, speech chat is back up over here. So we might actually have some sound. Maybe, maybe not. There we go. There we go. So, oh, Bella wants to say hello. Hello, Bella. I got a good lecture, Bella. Look, little Bella. This is my 4-year-old puppy right here. This is Bella. Oh, she's Bella. Anyway, okay. Introductions are over, Bella. So, induced voltage is a result of flux cutting across a conductor, and we'll talk more about this. But as there's a magnetic field, as the flux or the lines of force cut across a piece of wire, there's a current flow that goes through it, and there's a way that it goes through and stuff. You have to have some type of motion for this to take place. It can't just be a static field. There has to be some type of, well, an AC voltage. You know, it goes up and down, so the current flows back and forth basically. And that change is what the variations in current level or amplitude is what it's talking about there. So as that current moves or as that voltage moves, you know, you have to have some movement, whether it's a physical movement or whether it's AC moving it. So anyway, we'll talk more about that. So that ability is called self-inductance, or just simply inductance. Oh, and over here. Oh, the other way. So induction is basically by varying the current that results from a change in the current and not the current itself. So it's that change, okay? It's like, for instance, if you had a DC voltage and you applied it to a coil or to a wire, you might maybe have a spike of inductance, but then it stops because there isn't a change. So, and the faster the current changes, the higher the induced voltage is. So that's something that's also that's also a point. So if you look at a sine wave like so, at point A the current is 0 and there's no flux. So right here there's no magnetic field or flux, and then at point B, in the positive direction, there is some field, right? And then as it goes along to C, you get more, right? And then you get less again, and then you get a little bit less. And notice though that as it goes from positive to negative, here, see as the wave goes down to 0 and it goes to negative, well, no, a solar panel works off of changing the light into electricity. This is actually electricity inducing current flow in another pair of wires. So the direction of the flux or the field changes basically from a counterclockwise to a clockwise position. So the magnetic field of an alternating current is effectively in motion as it expands and contracts with the current variation. So as the current changes, so does the magnetic field and the direction of the magnetic field. So over here, we see that point C has maximum current, right here, okay, and the maximum counterclockwise flux. You're right there, counterclockwise flux. And then at point D, there's less, which is right there, but still counterclockwise. Now the field's collapsing because of reduced current, right? So as it goes negative, then it starts up the other way, and it starts going the other way, until you get to more negative voltage here, or current here. And then, as you can see, a little bit less, so it slows down. And this is, of course, over time. With point E, the current flow, where's point E? Right there, is 0. There's no magnetic flux, as you can see. The field can be considered collapsed into the wire. There's none. The next half cycle of current allows the field to expand and collapse again, but the direction is reversed, which is what I was saying. So like if you start here, it's going counterclockwise. It gets to 0, it collapses, and then as it goes negative, then it goes clockwise. So characteristics of inductance are important in AC circuits. In the circuits, the current is continuously changing and producing an induced voltage. So if you think about it, you know, that current's constantly changing, right? So if there's a piece of wire here, the current is cutting through it, right? Well, it's creating a current flow here. With a DC circuit, if you take, you know, a battery, there's no change. The only real way this could change is if I go like this with the DC voltage and change it, which I'm not really doing anything anyway. But in other words, if there's motion back and forth. So DC circuits that are turned off and on, and that's what I was saying, you know, you're getting current flow and you're stopping current flow, getting current flow and stopping current flow. That's when you can produce an induced voltage in a wire. Whereas AC, because it's constantly changing, you get an automatic change back and forth. More coffee. So the symbol for inductance is L, for linkages of magnetic flux. Kind of reminds me of a flux capacitor on Back to the Future. And there might have been something to do with that. I'm not really certain. But the formula for that inductance or linkage is L is equal to V sub L divided by DI divided by dt. So VL is the volts. DI divided by T is the current change in amperes per second. And the Henry, or the H, is the basic unit of inductance. 1 Henry causes 1 volt to be induced when the current is changing at the rate of 1 ampere. You know, and it kind of seems like everything we talk about is usually 1 to 1 to 1, right? Because we have to have some type of base for it to start at, you know. So 1 Henry causes 1 volt to be induced when the current is changing at the rate of 1 ampere per 1 second. The inductance in coils, and we're still talking about, you know, self-inductance, if I can hold the mouse button right. The inductance of coils, the inductance of a coil depends on how it is wound. So the way you actually wind it is how it's more efficient, or less efficient for that matter. A greater number of turns as you increase that L, you know, you have better output, because you actually have more wire or more turns that are there to be able to induce proportionately more current into it. So more area is enclosed in each turn, which increases L. Bella's even wondering what I'm talking about here. Yeah, she just wants attention. That's all. The L increases with what's called the permeability of the core, and we'll talk more about that here in a second. The L decreases with more length for the same number of turns, as the magnetic field is less concentrated. So L increases with the permeability of the coil, and L decreases with more length for the same number of turns. So if the turns are wrapped up, you know, really closely together, you're going to have more available wire together. Whereas if you take that same piece of wire and you stretch it out, then they're not as close together. So calculating the inductance of a long coil, an air core symbol looks like this. That's the symbol for a coil. That's called air coil. Doesn't have a core like this in here. Whereas these are the turns of wire. This is perhaps maybe a piece of a piece of iron of some kind. The symbol has these 2 little dashes or 2 little lines up on top of it with the coil symbol depicting an iron core, and then this right here is the formula. Inductance is equal to micro R, which is this, N squared times A divided by L, 1.26 times 10 to the negative 16 henries. So L is the inductance in henries. There's our L right there. Micro R is the relative permeability of the core. In other words, how you can go through the particular material. Somebody look up permeability and and put the definition of permeability in there, if I can keep this in my ear. And I fight with this every time, don't I? It's like I don't ever learn. Actually, I don't ever remember until I sit down right here. UR is the permeability of the core. N is the number of turns in the coil. A is the area in square meters, which is this one. And then L is the length in meters. So depending on the length, the permeability of the coil, the number of turns, and the area, that's what makes this part of the formula. And it's just 10 times 26 times 10 to the 6th Henry. So that's a formula that you'll probably need to know if you want to calculate the inductance. So is somebody looking up what permeability means? A typical coil inductance values. Air core coils for RF applications have L values in millihenries and microhenries. Again, milli meaning what? Thousandth, and what does micro mean? This should be the same to you guys, right? 0.001 and 0.000001 micro. Practical inductor values are in these ranges from 1 Henry to 10 Henries for iron core inductors. And then, like we were saying, in millihenries, 1 times 10 to the 3rd Henries or microhenries, which this really probably needs to be that right there, not this. Microhenry, which is 1 times 10 to the negative 6, which is a pretty small value. The formula, V sub L equals L, dy divided by dt, is well, voltage, right? And then induced, which is induced voltage, which is proportional to the inductance. Let's see. Oh boy. Yes. Very good, very good. So basically, it's how permeable it is. In other words, the measure of the response of the medium to the magnetic field, and it's the ratio of the magnetic flux density to the medium field strength, measured in henries per meter. Very good. That actually sounded pretty good on the chat bot. Sounded very collegiate. So that's how you calculate induced voltage, which is what V sub L is. Boy, maybe I shouldn't be drinking coffee, you know. So the energy is stored in the field, and you probably have seen something like this, especially if you put like little iron filings and stuff around a magnetic field. That is the actual energy or the magnetic lines of flux. And if you see this is a battery, that's a switch, and this right here is the current flow. Current flows in this circuit like this, and then it generates those fields right there where the energy is in joules. L is the inductance in henries, and L is the current in amperes. Hello, Chav, how are you? We're just kind of talking about permeability, and right now we kind of went to talking about the energy stored in fields and the different formulas. The different formulas. MChav is a TAT streamer and does beautiful drawings and does all sorts of other you can say what they are, MChav. I forget what it's actually called, but stuff with needles and really cute stuff. Really cute stuff. Right now, she's doing something like Inktober, working on day 7, right, Amchav? I'll let you chat about that if you want. Um, anyway, um, so here we have, like I said, the energy stored in the field, and then that's the formula for it. Um, Lenz's law, which there's a bunch of laws, right, in physics and in science. Tatting lace. Thank you. Lace is what I couldn't remember. Yes, and some very nice stuff too. Oh, okay, okay. I thought you were on day 7 of October, and anyway, never mind. Um, gotcha though. Gotcha though. The polarity of the VL depends on the direction of the current variation dy or di. So the direction here varies depending on that. So Lenz's law states the induced voltage produces current that opposes the changes in the current causing the induction. The polarity of VL depends on the direction of the current of the variation. You're very welcome. When the DI is increased, the VL has a polarity that opposes the increase in the current. When the DI is decreased, VL has the opposite polarity to oppose the decrease in current. So in both cases, the change in current is opposed by the induced voltage, and DI is the induced voltage, obviously. So that induced voltage actually works opposite on it too. Then there's what's called mutual inductance, which occurs when the current flowing through the conductor creates a magnetic field which induces a voltage in the nearby conductor. And this is what we were talking about earlier. So if you have two coils sitting next to each other, those coils have a mutual inductance of 1 Henry. When a current of 1 amp is going through there, it'll induce a voltage from this coil to this one of 1 volt. And that's what's called 1 Henry. And the formula is LM, which is equal to K, the square root of coil 1, times the square root of coil 2. So the coefficient of coupling, K, is the fraction of the total flux from one coil linking to another nearby. Specifically, the coefficient of coupling, not couplings, but coupling, K is equal to the flux linkages between L1 and L2 divided by the flux produced by L1. So there's no units for K because it is a ratio, basically, of the two values of the magnetic fluxes. The value of K is generally stated as a decimal value. The coefficient of coupling is increased by placing coils together. So if you have them far apart, then that ratio isn't going to be as strong, right? Because they're not going to affect each other. Possibly if you wind one on top of the other, okay, by putting them in parallel, or by winding the coils on a common core, that'll also help. What Belle is? I've been petting her the whole time we've been sitting here. A high value of K, called a tight coupling, allows the current in one coil to induce more voltage in the other coil.
Something went wrong. Uh-oh. Please try again.
Something went wrong, huh? How about if we just turn you off? That's what went wrong. I have no idea why my phone started talking to me. So loose coupling allows a loss of the value of that K and basically has the opposite effect. So two coils might be placed perpendicular to each other and far apart for essentially zero coupling to basically minimize that interaction between the coils. So it's like, it's like putting two wires together, and let's say there's a magnetic field here and a magnetic field. It'll affect the other one, but as you separate them, they'll not induce as much in the other one. So this is loose coupling here. Yeah. Yeah. Yeah, the phone had to act up, so she had to also. So here's an example of loose coupling. Here's two coils. Stands for coil, right? And this is what it was talking about if they're on the same uh, core and they're not as close together. Here's tighter coupling, right? So they're closer together. So they're going to induce a little bit better. This is what's called unity coupling, which you've got the flux going around here, and this is actually metal, probably more than anything else. This is zero coupling right here. They're perpendicular to each other, which is what we were just talking about a second ago. Let's see, examples of coupling between coils. Yeah, on paper or plastic from an air core. That's A right here. B would be wound over L for a tighter coupling. Let's see, that's this one here. And then for tighter coupling, K is 3, right? I guess L and L2 are on the same iron core, which is right here. And then zero coupling between the perpendicular ones with air cores. Notice there's no core at all there. So when we calculate L sub m, which is mutual inductance, increases with higher values for primary and secondary inductances. Then L sub m is equal to K times, we kind of talked a little bit about this, right? About this formula. The square root of L1 times L2, where L1 and L2 are the self-inductances, self-inductance values of the two coils. K is the coefficient of coupling, that's K, right? And Lm is the mutual inductance. So that's how you calculate the mutual inductance for that there, right? That's a better example of what we're talking about. So transformers, and we use transformers all over the place. There's transformers inside your microwave. There might even be transformers in here. There's certainly transformers in the chargers that lead up to here. But there's transformers all over the place in power supplies and stuff. A transformer's got two mutual windings of inductance. The primary winding is connecting the source of AC. That's the one you plug into the wall, right? And then the secondary winding is the one that's connected to the load, or that's coming in here. This being the load, right? So when you're charging using a phone charger, you get a little transformer that's plugged into the wall. Those are the primary windings, and then the secondary comes here. And there's also, well, we'll talk about step up, step down transformers here in a second. I believe, I don't know if this is figure 1911, but this is probably an iron core transformer. There's probably a core in there. Yeah. Well, you've used these type of transformers. Those are really common, and they're all over everywhere. They're all over everywhere. So this just happens to be a package, an easy package, that. But the let me see something. Actually, looking. I don't think I have one in here. I was going to say that little plug into the wall is a transformer. Yeah. Hold on a sec. Let me look at something. Yes. And they make things where you can't take them apart anymore. I was hoping I could somehow take this apart, but I'm not. And this is a good transformer, but the primary of this is probably connected to a transformer, and then the output or the secondary is probably connected on this side. I'm almost really tempted to take this apart, but I probably would ruin it. But one of these days I will take one apart, I guess. Just seeing if I have anything else up here that I could butcher. And I don't. But anyway, let's go on. We talked about primary windings connecting to the source and secondary windings connected to the load. So the transformer transfers power from the primary to the secondary. Here's kind of an example. This is plugged into an AC source, and it goes to the primary turns. And then the load is over here, and this is the secondary turns. Now, I want to point out, yep, that's right. They're glued some way. They don't want you to take them apart. And there's probably no need to fix them. You know, you probably get it, what, for $7, $10, and you got a new one, right? I mean, that's our society. In this case, here, transformers step up voltage to 100 volts and steps current down to 1 amp. So in this circuit here, this coil and this right here is a core, probably an iron core. This circuit here probably runs about 10 amps, right? You got 10 volts here. You have 10 turns here. And then the induction that takes place goes across. You know, the magnetic lines of flux go across to induce over on this side. And this side's got 100 turns. This gives us 100 volts and 1 amp of current. Of course, load is 100 ohms. But the point is that it steps the voltage up. I was going to say, how is Kilroy hosting Peeper for 0 viewers? Well, that was Twitch. That's funny. Maybe I should be hosting myself on YouTube from Twitch. But anyway, it doesn't matter. So that ratio of 10 to 100, that's actually a step-up transformer. And it's a 1 to 10 turn ratio, right? So that's a 1 to 10 transformer. And it what am I trying to say? It steps up. It steps up. Nah, I'm not going to do it. I'm not going to do it. Had I thought about it, I would have. So had I thought about it in the beginning, I would have. So a transformer can step up or step down the voltage levels from the AC source. So you can have a transformer device that's concept mutual inductance to step up or step down an alternating voltage. Notice it's an alternating voltage, right? So we've got a primary here and a secondary, and the primary's got less turns than the secondary, so that's a step up. The voltage load is less than the voltage source, or greater than, I'm sorry, the voltage source. And then with a step down, the voltage load is less than the voltage source. So notice here we've got more turns than on this side, and it's visually the way it should be. So this is a step up, this is a step down. Now, just by chance, if here the voltage is going up but our current is going down, and by the way, the power has to be the same on both sides. I don't understand what you mean by Wiki has a transformer, but here's the point I'm trying to drive. The power has to be the same on both sides. The calculation of current times voltage on both sides has to be the same. So if over here we had 10 volts, we'd have 10 amps. Over here we'd have 100 volts and 1 amp. That would be our 100 watts on both sides. The same thing here. So if we had 100 watts over here, we'd have to have 100 watts over there. So if we have 100 volts here, then this one would step it down to 10. If we had 100 volts here, I'm sorry, and 1 amp of current, this side would have 10 amps and 10 volts. Oh, wait. Let me see this. Wiki has a transformer all his own. I'm still lost. Okay, yeah, don't tell me. Anyway, so turns ratio, the ratio of the number of turns of the primary to the secondary. That's what's called the turns ratio of the transformer. And then the turns ratio is equal to N sub P divided by N sub S. Okay, so number of turns on the primary divided by number of turns on the secondary. Okay, I mean, that's what that stands for. The turn ratio N sub P divided by N sub N is sometimes represented by the lowercase a. So, you know how they like to do things like that, right? So voltage ratio is the same as the turns ratio. It's a beautiful transformer. Hold on a second. Sorry, guys, but I got to do this. You mean like this right here? I don't know. You probably can't see it because of the green screen, but this is a Mustang beautiful transformer. But anyway, enough of that right there. It's the B, huh? Is that what you're saying? It's the B, the orange Camaro in Transformers. Is that what you're saying? Since you said it's a beautiful. Yeah, see? You thought I didn't know what you were talking about. Yeah. Well, I didn't, but then after I got to thinking about it, you know, I'm like, okay, I get it now. Yes, yellow. Yes. And I know the yes, Ruben, I got it. Yes. And really I got to thinking about this one and got to thinking about the Camaro, right? This happens to be a Mustang. Ooh. Anyway, so the voltage ratio is the same as the turns ratio. It's V sub P divided by, thank you, V sub P divided by V sub S, which is equal to the number of turns on the primary divided by the number of turns in the secondary. Okay, so anyway, we go forward. When a transformer efficiency is 100%, the power on the primary equals the power on the secondary. And if the power rating is less, okay, which is reality, okay, power ratings refer to the secondary windings in real transformer efficiency as less than 100%. So, you know, it doesn't, because you're going to have some type of loss somehow, some way. But a perfect transformer is 100% efficiency. In other words, the power on one side is the same as the other. Okay, so here's some voltage ratios. A step up of 1 to 3. Got 120 volts on this side. A ratio of 1 to 3. We have a load over here, and it doesn't matter really what the load is. We've got 360. We have 360 volts on this side. Give me a second. When a step-down transformer is 3 to 1, it's 300 turns or whatever the number to a third that count over here. Notice the voltage is a third. So if this is 120, this is 40. It doesn't matter what the load is, but this is just like a series resistor, right? Right there on that load is where that voltage drop is. So that's what these two numbers turn out to be. Now, what's your question when a girl has no name? And I guess there's a little bit of a delay, so does anybody else have a question too? We can make this question time. In fact, if anybody has any questions throughout the lecture, the stream, I don't know what you want to call it, but I guess it's a lecture. I'm waiting. Back up one page. Okay, we backed up one page. Okay. That's not a question, that's a statement. or a command, actually. You get it. Or is it now I get it? Friends? Okay, I'm gonna go forward a page and then I'll come back after you ask the question. So the current ratio is the inverse of the voltage ratio. In other words, the inverse, right? The upside down, right? That is voltage step up in the secondary means that current steps down. So if the current goes up, the voltage is going to go down in the secondary. If the voltage goes up, the current's going to go down. Isn't that what I just said? But anyway, the inverse. Well, it's voltage on the primary divided by voltage on the secondary. You had it. Okay. No, I get it. You had it. And then the number of turns on the primary is the number of turns in the secondary. Yeah, it has to be. It has to be, especially if you're comparing the turns and the voltages, you have to say the voltage on the primary and the turns on the primary, and because it really is the same. But they match is the thing. You can't say the number or the voltage on the primary and the voltage on the secondary is the ratio, but the number of turns on the secondary divided by the number of turns in the primary, because that wouldn't match. It has to be the matching number of turns in the primary, voltage on the primary, number of turns on the secondary, voltage on the secondary. That's the ratio. I mean, it's yeah. You can't get them backwards. It has to be that way. Yes, yes. It is exactly like a ratio. It's exactly like this right here, 1 to 3. And that's a really good question, actually, because that's the whole point of the 1:3, like that. See, 120 volts. Oh, we only have, let's say, I don't see the actual turns. Let's say we have 100 turns right here, and we have 300 turns here. You're welcome. So if we have 120 volts here, then we're going to have 360 volts there. Yeah, it can burn all right if it gets hot enough. Yeah, but just like here, this is a 3 to 1. We have 3 times as much voltage over here, 3 times as much turns over here as over on this side. So yes, good question. Good question. And likewise, this is the same. This is the current ratio. So if we have 0.3 amps over here, then we're going to have 0.1 amps over there. If we have 0.1 amps here, we're going to have 0.3. Because remember, it's the inverse now. If we have more voltage on this side, we're going to have less current. If we have less voltage, we're going to have more current. And actually, that's a function of Ohm's law, because if we say, okay, we're going to produce 10 amps, well, if you go up on the voltage on this side, we got 10 amps over on the primary side, right? To produce 10 amps over here, that current's going to have to be smaller because we got more voltage. Because oh yeah, exactly. It's just like a scale for a model house, yeah. But the current is the inverse to the voltage here. The current ratio is the inverse of the voltage, which is really what it said here. Current ratio is the inverse of the voltage ratio. That is, voltage step up in the secondary means current step down and vice versa. Yes, sir, or yes, ma'am. So transformer efficiency is the ratio of the power output to the power in. So stated as a formula, the percent efficiency, power out, divided by power in times 100. So assuming 0 losses in the transformer, power out equals power in, and the efficiency is 100. Woohoo! But the actual transformer efficiencies are somewhere between 80 to 90%, which is acceptable, But yeah, if you could get a power transformer that's 100, boy, that'd be great, So transformer efficiency. This is talking about power on the primary. 120 volts times 100 or 0.12 amps equals 14.4 watts. So if you have 0.3 amps on this side, the load is 40. 40 times 0.3, 12 watts. So in this case, we've got a power on the secondary divided by power on the primary, an efficiency of 12 divided by 14 times 100, 83% efficiency. Primary power that is lost is dissipated as, you guessed it, heat on the transformer. You know, it's just like mostly anything. We lose a lot of efficiency through heat. In our cars, it's the same way. The fuel we burn, a lot of it goes out the tailpipe. You know, it's just one of those things. So loaded power transformers, loaded. Yeah, they've had a little too much to drink, right? Calculated voltage source from turns ratio and voltage primary. Use the voltage source to calculate the current source. So basically what that's saying is all these formulas. How do you calculate? Use current on the secondary to calculate power on the secondary. Power on the secondary is equal to voltage on the secondary divided by or times current on the secondary, which is actually, when you think about it, Ohm's law, right? Power is equal to voltage times current, or pi, right? Use power on the secondary to find the power ratio, right? Which is power in the primary, which is equal to power in the secondary, right? And then finally, the current at the primary can be calculated. Current at the primary equals power at the primary divided by power voltage on the primary. It's just a matter of piecing it together in that sense. You know, what do you have? Okay, like here we've got voltage at the primary. We've got current at the primary. Hey, we've got 132 watts here. Over here, we've got, and this is a unique transformer, sometimes called a center tap transformer, but or a multi-tap transformer. This one has two coils on this side, but with two different circuits. This one's got a coil on this side. Voltage 1 is 720 volts over here, and we know the load is 720 ohms. So by doing Ohm's law, voltage divided by resistance, we get current, 0.1 amps. Power is current times voltage, pi, right? Current is 0.1. Voltage is 720. Then our wattage is 72. On this side, hey, we got 6 volts. We've got 0.6 ohms. Hey, we got 10 amps. Power is voltage times current. 6 times 10, 60 watts. On this side, 72 and 60. How much is that? Who can add that up? Come on, you guys add that up. What's 72 plus 60? As we scramble for our calculator. Yes. How come I didn't hear that? It came out over there, but didn't come out over. Oh yeah, it did come out over here. Yeah, 132 exactly. So this is 132 watts over here and 132 watts. What's the power ratio on here then? 100%, right? On that one. It's just an example though. So auto transformers. And this is not an auto transformer, okay? An auto transformer is a transformer. Yeah. You did that in your you did that in your head. Thank you. Yes. An auto transformer, again, not one of these, is made from one continuous coil, and then it's tapped with connections between the end terminals. An auto transformer has only 3 leads and provides no isolation between the primary and the secondary. Ooh, did you hear that? No isolation between the primary and the secondary. Ooh, excuse me. Like I said, maybe drinking the coffee wasn't a good thing. Transformer voltage, current, and power ratings must not be exceeded, excuse me. Doing so will destroy the transformer. Some typical ratings, voltage values are specified for primary and secondary windings. So, I mean, everything's got ratings, right? You've got a current rating, you've got a power rating, you've got a frequency. Those should not be, they're there for a reason, right? It's just like the speed limit on the road, right? Yes. So is this an Autobot or a Decepticon? So voltage ratings, and manufacturers always specify the voltage rating on the primary and the secondary windings. Under no circumstances should the primary voltage rating be exceeded. What would you think if the primary voltage was exceeded? What would you think would happen? Well, I'm rhetorically asking the question because if you have more voltage, wouldn't you think that there would be more current, right? And guess what? There may be even a fire that induces because of it, because of overheating and stuff, because of a lot of current or more current than what's supposed to be. Well, yeah, it would be a deception for sure. Oh, this is a Decepticon? Okay. So in many cases, the rated primary and secondary voltages are printed on the transformer, right? So regardless of how the secondary voltage is specified, the rated value is always specified under full load. In other words, if it's the maximum that it's always going to be used when the rated primary voltage is applied. So those are the maximum amounts according to the ratings. So current ratings, manufacturers usually specify current ratings only for the secondary windings. If the secondary current is not exceeded, there's no possible way the primary current can be exceeded, right? Because remember, it's that ratio. So they say, okay, you can only have this much current on the output, and that's what's used in calculations. If the secondary current exceeds its rated value, excessive I squared R losses will result in the secondary winding. So what's I times R? Current times resistance is what? Well, current squared times resistance is what? I'll let you guys figure that out here in a second. What is I squared R? Anyway. So the power rating is the amount of power the transformer can deliver to a resistive load. The power rating is specified in volt amperes, or VA. The product VA is called apparent power since it's the power that is apparently used by the transformer. How about that? Apparently used by the transformer. The unit of apparent power is VA because the watt is reserved for the dissipation of power and resistance. Typical ratings for power transformers are 50, 60, and 400 hertz. A power transformer with a frequency rating of 400 hertz cannot be used in a 50 or 60 hertz environment because it will overheat. You remember we were looking at oscilloscopes and sine waves. So it goes up and down like this, right? And it would be going so much faster than 60 hertz. So it'd be going so much faster that it would induce the voltage faster, right? I mean, you would think, right? And that's mainly the reason, actually. So power transformers with a 400 hertz ratings are often used in aircraft because these transformers are much smaller and lighter than 50 to 60 hertz transformers. When I was in the Air Force, we had 400 hertz aircraft. I mean, it says it right there, but that was one of the things that we used to talk about. Why do they use 400 hertz in our, I think we called them, I want to say plush, but that's not right. But anyway, there were these big trailers with chargers. Hey, Danny Mac, how are you? And we would plug them in, and they were 400 hertz. But the reason we use the 400 hertz is because of the size. The rating was smaller because you fly an airplane. Well, you can save that that weight. You doing okay, Danny? So transformers are often used to change or transform a secondary load impedance, and we'll talk about impedance, to a new value as seen by the primary. The secondary load impedance is said to be reflected back into the primary, and it's called a reflective impedance. The reflective impedance of the secondary may be stepped up or down. And the equation for the reflected impedance is impedance on the primary, the number of turns on the primary divided by the number of turns on the secondary squared times the secondary impedance. So that's how you calculate the reflected impedance. If the turns ratio, number of turns on the primary divided by number of turns on the secondary, is less than 1, the secondary impedance will be stepped down in value. And I mean, that's what it is. Transformer impedance matching is related to the turns ratio. So if you have number of turns primary divided by number of turns secondary, then doing great, Danny, doing great. Well, actually, a dryer uses the same frequency, 60 hertz, right? It might be, the voltage might be different phases. In other words, if it starts here, the second 120 volts might start here, okay? But not faster, just a phase off maybe. And then you have two circuits of 120 volts. And the way it's wired too might be different. Some industrial machines have three phase. Some businesses actually have three phase. And again, it's just where it starts, where that sine wave starts. The next phase might start, or the next one might start offset a number of degrees. And honestly, I don't know what the number of degrees offset. I think it's 90, but I'm not. It might be 120. I don't remember, to be honest. Transformer impedance matching is related to turns ratio, like I said, but it's a square root of the impedance on the primary and the impedance on the secondary. The impedance ratio is like this: 1 to 3. The impedance ratio is 1 divided by 9. So because it's the square root, right? So if it's 1 to 3 here, it's going to be 1 to 9. The same thing here. If it's 3 to 1, it's going to be 9 to 1. This load is the load on the source is 1 ohm, and then the load on the source is 81 ohms. Look, the load on the output or on the secondary is 9 and 9. So it kind of flips it around. Impedance matching for maximum power transfer. Transformers are usually used when it's necessary to achieve a maximum transfer of power, okay, from a generator to a load, when the generator and load impedances aren't the same. So if the impedances aren't the same, the transformer kind of matches it up. The application is called impedance matching. I mean, that's what it is. It matches the impedance on one side to the other. It's kind of like you have and man, I don't even know, does anybody have stereos anymore? But you would have, 8 ohm speakers and 4 ohm speakers, and actually they were used for different things, but you wouldn't use a higher ohm speaker because then there would be an impedance match, which would mean the current would be all messed up, and maybe even the sound, maybe even the voltages and stuff, maybe even, damage the unit. So you wanted to match those impedances. Thanks, Michael. 120. Yeah, I couldn't remember if it was 90 or 120, but thank you very much. So that's the application of a transformer being used in impedance matching. And this is what I was talking about earlier with an amplifier. Okay, the transferring power from an amplifier to a load. The amplifier has whatever the resistance, which is like 200 ohms, and then the load's got 8. So you you would need to match those, or else what? It's not right, right? Let's see here. So, whoa, this one's interesting. Connected as shown, the load receives 1.85 watts of power. So if we had that 200 ohms over here, and we had 8 ohms over here, PL, VG, let's see, VG is the source voltage, right? Squared, I mean, this gets pretty complicated, right? Times the load resistance, plug all those numbers in, times 8 ohms, 1.85 watts of power. I'm not going to calculate it, but I wonder if we took this to 16 ohms, what it would do, right? It would be 200 plus 16 times 8. This would definitely change, right? But that's mainly why we don't use, speakers unless they're the right impedance. Connection shown increases the power delivered to the load. What did they do here? Using a transformer to make the 8 ohm load resistor appear like 200 ohms in the primary. Oh yeah. What they did is they matched it, okay, with a transformer, so that, because remember, my lost my mouse. 12.5 watts in this case. On both sides, because they match, right? Whereas, what was it on this one? 1.85 watts? Is that right? This gives you more power out, doesn't it? This is mismatched, 200 ohms, right? And 8, but this one matches it up, and you actually get more power. Some impedance transformations. These are turns ratios. Remember, the number of turns on the primary divided by the number of turns. 8 ohm speakers deliver more power and better sound than your average speakers. Yeah, I've seen some with 4 ohms too, and I've seen some with 16 ohms. Have you ever used any with 4 ohms? And I can't remember. I mean, this has been a while, guys. I'm not an audiophile, but I almost remember that if you even went smaller in the ohms, that you would actually have better sound. But like I said, I'm not an audiophile. But 8 ohms is probably the standard, right? Cool beans. So this right here, this matching is 5 to 1. So eddy currents, not to be confused with Eddie Van Halen, right? Eddy currents are introduced in an iron core transformer, or an iron core of an inductor or transformer. And what eddy currents do is they increase the temperature, which is wasted power, okay? And it causes a loss of frequency. What can you do about them? I don't know. What can you do about them? You guys probably could tell me. Here's a cross-section view of an iron core showing eddy currents. So as the current flows this way, the eddy currents flow in this direction. Do you think it helps, or do you think it hinders? I mean, if it oops, wrong way. If it gives you an increase, losses with increase with frequency, eddy currents raise the temperature of the core, so there's heat, right? There's wasted power there, right? So I mean, you don't get something for nothing, right? It has to come from somewhere. And then of course you get losses with frequency. So with those eddy currents, you would lose power. They're what's called core losses. Hysteresis, depends how you want to pronounce it, right? Is the loss resulting from additional from additional power needed to reverse the magnetic field. So to get it to go back the other way, then you have to spend more energy trying to get it to compensate, or trying to get it to I guess compensate's the word I want to use. The greater the frequency, the more of the loss is there. If you don't have a core, though, excuse me, if you don't have a core, there's no loss, right? Because there's none of that flow in the core itself. So air core transformers practically have no loss. And like this says, though, this is the other end of that. Yeah, if you don't have any loss, that's great, but without an iron core, you can't increase the field, so you really don't have that much inductance. You're limited to low values, but they're still used in circuits and stuff. You have in the range of millihenries or microhenries. So losses can be reduced by using a laminated core or powered iron core transformer. So if you have to have a transformer like that, then what you do is you have a powered or laminated core. The type of steel used can reduce the hysteresis. What? I'm having a hard time with that. Loss. The most common type of insulations are a laminated core, a powdered iron core, or a ferrite core in between, the coils. A laminated core is a shell-type core formed with a group of individual laminations, and I've seen them. They look just like that, like little pieces of metal put together, like little E's maybe, or all put together. And then powdered core is basically individual insulated granules pressed together in the form of a slug. And I wish I had one, but I don't. I don't have any transformers here at the house. Ferrite core is a synthetic ceramic material that's also ferromagnetic, or that can magnetize. So those are types of cores. Now, to vary the inductance, and I was kind of thinking of a choke or something like that. A coil may be varied in a couple of different ways. For larger coils, more or fewer coils can be used to one tap. In other words, you can move it back and forth. You can have some type of slider coil that can vary the number of turns. I've even seen the core go in and out, in certain tuning circuits, to where you can turn it and it moves inside. So there's various different ways that you can vary that the inductance. So figure 1924 shows that the schematic symbol for a coil with a slug of powdered iron or ferrite. So that's kind of what it looks like. Usually an arrow at the top means that the adjustment is at the top of the coil. So you can usually adjust it, and like I said, in certain circuits, I've seen them in TVs and stuff, and in radios too, where they'll have a slug. It kind of looks like an Allen screw that you just take and you just turn, or in certain circumstances you maybe use some type of plastic device, so if you're adjusting it in the circuit, it doesn't electrocute you, it doesn't affect it also. But that's an adjustable slug, a method of varying inductance, I guess. To get different inductances, to get different values of henries, to vary the henry, to vary the inductance, to vary the magnetic field also. I mean, in essence, not the frequency itself. But that's a good question. The symbol in figure 19.2D, or 1924D, sorry, this one here, is a variometer. Variometer, which is an arrangement for varying the position of one coil within another. The total inductance of the series-aided coils is minimum when they are perpendicular. Henry or inductance? So as you change this from perpendicular to parallel is how you vary this one, how you vary the inductance this way, because like it's saying there. So with the arrangement, the position of the coils within each other. Yeah, well, but isn't that and what material are they made out of? Because normally when you're adjusting it, right, and you're calibrating it and you're looking at different readings and stuff, are they not? Are they not um, plastic? Are your tools not plastic? Or are they some other non-ferrous material maybe? Ham-fisted, huh? Anyway, I'm going to go on because what we're saying here is that as the coils change, the inductance also changes. So that's another way to vary the inductance. You know, I don't know if I've ever seen anything like this, or maybe I just haven't realized it. Um, I mean, I've seen capacitors, that the plates change, but I don't think I've ever seen coils that change. Maybe I just haven't. And I'm not pretending that I know a lot about radios or a lot about internal circuits like that. But I don't know. Maybe I have and just haven't really paid attention, or maybe I haven't seen the inside of a can or something like that, and that's what it was actually happening. Um, I want to have to dig up some old stuff I've got out in the shop. So for any method of varying the inductance, the coil with an arrow is used. And it looks just like that. Kind of like a potentiometer, right? It's got an arrow in it and a resistance in the case of a potentiometer, right? Um, but that's a method of varying a coil right there on a schematic circuit. The variac is an auto transformer with a variable tap to change the turns ratio. A variac. The output voltage in the secondary can be varied from 0 to approximately 140 volts with a 120 volt 60 hertz input. So that's a variac. You guys ever seen variacs? So with no mutual coupling, for series circuits, you know how in series resistive circuits you add up the resistances in series, and in parallel resistance circuits, right? Look at these formulas. So for series circuits of inductances, you add the inductances just like you would the resistances. So inductors in series, you just add up the inductances. And then for parallel circuits of inductors, in other words, you've got a coil here and a coil here, instead of a coil, behind another coil, you've got a coil here and a coil here, use the inverse formula. The first one says the total inductance, and the second one is the equivalent inductance. So L sub EQ is equal to inductor 1 plus inductor 2 plus inductor 3, the inverse of that. And of course, it goes on forever, right? Which is the same formulas or similar formulas that series circuits and parallel circuits use. So that's an easy way to remember the inductances, or the formulas for those two. So series coils for L sub M. L sub M depends on the amount of mutual coupling and whether the coils are connected in series aiding or series opposing. Series aiding means that the common current produces the same direction of magnetic field for the two coils. Series opposing results in an opposite field. And can you think about it? I mean, if they're opposing, don't you think it'd be making it less, right? Whereas if it's the same direction, you'd be increasing it. So this is the wiring for series aiding, and this is series opposing. So the coupling depends on the coil connections and the directions of the winding. And the directions of windings do have an effect on it too. Reversing either one reverses the field. Reverses either one reverses the field. So to calculate the total inductance of two coils that are series connected and have mutual inductance, it's L1 plus L2 plus or minus 2LM. So the mutual inductance LM is plus increasing the total inductance when the coils are series aiding, or minus when they are series opposing, to reduce the total inductance. Energy in magnetic field induction. What is that? Oh, yeah. The magnetic flux of current is an inductance that has electric energy supplied by the voltage source producing current. The energy is stored in the field since it can do the work of producing an induced voltage when the flux moves. Remember, we were talking about transformers, right? And how one affects the other. You have to have that movement. The amount of electric energy stored is, the energy is equal to, is that epsilon? Which is equal to 1 divided by 2, Li2. The factor of 1/2 gives the average results of L in the producing energy. Stray capacitive and inductive effects can occur in all circuits with all types of components. And it's interesting because capacitance can occur with two wires, with two devices close together. A capacitor has a small amount of inductance in its conductors. A coil has some capacitance between its windings, again because they're close together, right? And anything that has some type of electrolyte in between it, there's some, I want to call it some capacitive or charge holding effects. And of course, it's not free. It has to come from something, right? A resistor has a small amount of inductance and capacitance. So a resistor's got kind of both. A practical case of problems caused by stray inductance and capacitance is a long cable used for RF signals, which is the case. You know, if you have really long cables, not only will you have signal loss, but you'll have capacitive and inductance problems that are caused by that. And they're stray. They're not intended. If the cable is rolled into a coil to save space, a serious change in electrical characteristics of the line will take place. I've always heard, though, that if you... Anyway, I'm not going to say what I was going to say. For twin lead or coaxial cable feeding the antenna input to a television receiver, the line should not be coiled because the added inductance or capacitance can affect the signal. Because you're basically like creating what? You're creating something else, right? A capacitor, a transformer. You know, if you have stuff together, I know that in running network cables, for instance, you run network cables in the ceiling. Well, if you run them right next to a power line this way, you're going to get inductance back and forth. You're going to get something generated, some magnetic field generating a signal in this cable. So you always want to have them like this. Remember what we're talking about? The inductance. The closer to parallel, the less it is. So imagine if you have it wound in a coil. They're all kind of like that, right? So as shown in figure 1929, a coil has distributed capacitance, or C sub D, between the turns. Right in there. Look at that. Look at that. Looks like a nice little capacitor too, don't it? Each turn in a conductor is separated from the next turn by an insulator, which is the definition of capacitance. I mean, it is. Each turn is a conductor separated by the next turn with an insulator, which is the definition of capacitance. The potential of each turn is different from the next, providing part of the total voltage as the potential difference to charge, C sub D, which is here. This results in an equivalent circuit of this right here. The L is inductance. The R sub E is the internal AC resistance. Pretty cool looking, huh? Equivalent circuit of an RF coil, distributed capacitance, which is A, and the equivalent circuit, which is right there. So that's kind of what it turns out to look like. So the resistance is the resistance in the cable. That's the coil, and then there's the capacitor. So as shown by the high frequency equivalent circuit in figure 1930. Is that 1930? No, that's 1920. Okay, so it's this one. A resistor can include a small amount of inductance and capacitance. So the inductance of a carbon composition resistor is usually negligible, which, it's just a regular old resistor. Wire-wound resistors, however, have enough inductance that it is evidence, because guess what? They've got wire that's wound, right? Whereas a regular resistor is just carbon, right? So many digital multimeters are capable of measuring the value of a capacitor, but few are capable of measuring the value of an inductor. I thought I had a capacitance meter around here, but I guess I don't have it in my mess, just sitting here. And basically, it's just two connections like this that you pretty much plug a capacitor in. So when it is necessary to measure the value of an inductor, a capacitor-inductor analyzer should be used. I don't think I've ever had an inductor analyzer, but I do have a capacitor inductor or capacitor. I'm kind of wishing I could just find it. Nope, that's not it. Nope, that's not it either. It's in one of these little tins, actually. But anyway, enough of that. Let's go on. So the capacitor-inductor analyzer can also test the quality, or Q, of an inductor by using a ringing test. Another test instrument that is capable of measuring inductance, capacitance, and resistance is an LCR meter. A typical LCR meter is shown in figure 1931, which was the previous slide. Yeah, they are. Man, now I'm trying to figure out where mine is, because I had them the other day right up here. And see, that's what happens when I put stuff away. Now I'm obsessing about it. Where is it? Where is it? Nope, that's not it. Yep. Yeah, as soon as I get off the stream, I'll find it. All right, so that was the previous screen that we just saw. So this is a handy piece of test equipment. However, most LRC meters only measure the value of a component. So the most common trouble in coils is an open. All right, I mean that's usually what happens. So as shown in the figure, an ohm meter connected across coil reads infinite resistance for the open. So if you got a coil, which is just a piece of wire, right? It's open. You have infinite ohms. I mean, it's simple as that. Excuse me. More coffee. If this coil were good, it would show resistance relative to what the resistance should be, what it would be rated at. Now, you might or might not know that, or at least easily know that, but if you have some resistance, it probably is right. Now, you might be measuring resistance within the circuit too, unless you pull it out of the circuit. But the point being is that if it's open, you'll see the open, or you'll see whatever resistance is really there. So if you say had, I don't know, 50 ohms, right, and you knew that it was a 50 ohm coil, or that's the value of it, if it was open, you'd have whatever the circuit resistance was at that point, but it would be open. If you had it out of the circuit, yeah, that's easy. It's open, you've got infinite resistance. So a coil has DC resistance equal to the resistance of the wire that's used in the windings, because that's all it is wire wound up, right? As shown in figure 1913, the DC resistance and inductance of a coil are in series. The DC resistance and inductance are in series. Although resistance has no function in producing induced voltage, it is useful to know the DC coil resistance because it is usually the inductance can also be assumed to have its normal value. So if it has a resistance, it's probably fine. It's not like it's going to go bad. What just happened? Did we just finish the presentation? No. I thought it was a little longer than this, which it's pretty long. Yeah, we did. So basically the point in this is that if you have a coil, it's going to have some type of internal resistance. I mean, that's basically all it is. Well, anyway, I've got one other thing to go over, and the PowerPoint's going to be in Blackboard, or if anybody wants me to send them the PowerPoint and the and this other deal, I'd be more than happy to send it to them. Just PM me. So in the labs, or in the lab, oh wait, you can't see this, can you? So in the lab folder are these labs. This one, that one, and there's a test in here too, by the way. And I can send you guys these if you want. Of course, if you have access to Blackboard, you can access it. But what I was gonna get to is in here, there's an inductance sheet that's a little more. Oh wait, that's the PowerPoint. Oh, I didn't put it in here. Transformers PDF. No, I think it's this one. Let me see. Excuse me. No, this is the lab. This is the lab, what we're going to do. Hold on. Let me find it. I guess I didn't put it in here today. But it's a little bit of a review to what we just said. Kind of more what really needs to be known. Good. Scope. Where was it? CT banner. Syllabus. Man, I could have sworn I put it in there too. PowerPoint's lab document. Combo circuits. Well, I'm going to have to bring up email. Hold on, guys. Let me open up my email. I know I've got it in email. And then what I'll do is I'll make sure I put it in there. And I probably had it in there, but anyway, here's a good transformer basic rundown. Kind of a review of what we just talked about. The transformer operation works on the principle of one coil, primary windings, secondary windings. Remember that ratio between primary and secondary, right? The current in the primary winding produces a magnetic field in the core, and there's a slight loss basically a leakage or flux. The magnetic field is contained in the iron core and coupled through the secondary winding. So there's a current induced here and here and there. Here's those eddy currents that we were talking about. The primary windings of a coil of wire supplied by electrical voltage to produce a magnetic field in order to induce a voltage to the secondary winding. And the secondary winding is a coil of wires or windings that move through the magnetic field to produce that are produced by the primary winding. Primary voltages, the primary windings of a transformer are designed to operate on the supply voltage. Typically primary voltages are 120, 240, 480, and they vary. I mean, they vary too. The amount of secondary voltage that is produced by a transformer depends on how many coils or windings are placed in the magnetic field produced by the secondary or by the primary windings. A small number of windings produce a small voltage, while this exact form the amount of secondary voltage that's produced by a transformer depends on how many coil or windings there are that are placed in the magnetic field that's produced by the primary winding. So in other words, whatever the secondary winding coils are, whatever that magnetic field, it's going to be inducing a current over in the other one. So a number of small windings produces a small voltage, while a larger number of windings produces a higher voltage. It's that ratio thing, right? A step-down transformer means that the secondary voltage is lower than the primary voltage. For example, a typical doorbell transformer is supplied with 120 volts, and it produces 20 volts in the secondary. It's stepping the voltage down. And then a step-up transformer, okay, a few transformers are called step-ups. That means that the secondary voltage is higher than the primary voltage. You plug it into the wall and you got 120 in there, right? Secondary voltage usually goes up to 10,000 volts, like in neon signs and stuff. The wattage of transformers is rated. Transformers are rated in wattage. If the wattage is exceeded, the windings can be damaged. To keep that from happening, then a fuse is placed, right? Like with mostly anything else, you put a fuse in place to keep, excessive current from being drawn. Primary of a 120 volt, 20 volt transformer is rated at 1,000 watts. To find the primary current rating of the fuse, you divide the wattage by the voltage. 1,000 watts divided by the voltage, hey, 8.3 amps. So I'm going to fuse it maybe for 8 amps, maybe for 5 amps, just depending on what the application is, right? The secondary of the transformer can also be fused. So if you're putting too much out on the secondary, you can use this in the same identical formula. How much amperage how much amperage is it safe to draw on that side? Turns ratio, the turns ratio of a transformer, the windings, the relationship between the primary and the secondary. Typical doorbell, 120 volts, 20 volts on the secondary, you have a turns ratio of 6:1. In other words, the primary windings has 6 times the number of windings that are on the secondary. And like I said, I'll put this on there also. It's probably kind of like a little cheat sheet, basically. Anywho, wow, I got bunches of these. Let me see what I got over here. So I guess I'm going to get big again. My ratio is going to increase. Anyway, thank you, folks, for being here. I really appreciate it. MChab, it was a pleasure to have you here. When a Girl Has No Name. Ruben, thank you for being here. Danny Mack, thank you for being here. And Michael Castle, thank you also. Guys and ladies, I will probably be doing another, I don't know what the topic's going to be yet, but on next Friday I'm going to be doing another lecture. And, you all are all welcome to be here and ask questions and You know, I may not know everything, and you might know something I don't. You might want to interject too. I don't have a problem with that. I appreciate that. You guys are awesome. You guys. You're welcome, Ruben. Welcome. No, you weren't. You weren't a disruption at all. Hey, that's what makes I think the lectures better when people actually ask questions. Now, you know, if you're asking why the sky is blue, it's a different story. But you know, you were asking questions that I think that contribute, makes somebody think. Maybe you know. Um, I can always ban you, friends. No, I'm just joking. But anyway, with that being said, I think I'm gonna just call it quits for the night. I don't even know what time it is. It's 10:30. So nah. The only question that's stupid is the one that's not asked. Okay, that's the only stupid question. Seriously and truly, I believe that to be the case. So nah, nah. Anyway, I guess with that, I will say see you guys in class. And no matter what you do it just for fun. I hope this was fun for you. It was certainly fun for me. But anyway, guys, live long,